Hey folks, this is chapter 11 and we only do a small part of chapter 11 in the didactic or lecture portion of the course. Most of this chapter is done in lab and you've already started it. You've already started the muscle system in lab. So here we go with the muscular system. First of all, we did this in lab, but just let's revisit this. The muscles have origins and insertions. And the origin is typically defined as the stationary bone, and the insertion is typically defined as the movable bone. Sometimes those can be reversed based on changing the movement. For example, shrugging your shoulders versus hyperextending your neck. They reverse the origin and insertion of the trapezius muscle. The prime mover of a given movement is the muscle that does most of the action, and they're called agonists or prime mover sometimes. And each muscle has an antagonist because muscles can only pull, they never push. Because they only pull, you have to have an antagonist to a certain movement. If you flex your forearm, you must have a muscle that extends your forearm. If you flex your leg, you must have a muscle that extends your leg, and these are called antagonistic muscles. Now, synergistic muscles are smaller helper muscles of the prime mover, and this is why athletes cross-train. So why would a runner start swimming? Because their swimming strengthens synergistic muscles to the running activity. Of course, they're prime mover muscles for the swimming activity, but they're synergistic muscles for the running. So cross-training helps to condition and build the synergistic muscles. And then some muscles are known to fixate a bone, so another muscle can actually pull on a stationary bone. Example of that would be the rhomboideus muscles hooked to the scapula, or the teres major and teres minor hooked to the scapula. And I mean, you got to hold the scapula stationary for a lot of your arm movements. Think of a baseball pitcher, sorry, a baseball pitcher, not picture, but pitcher. You know, he throws the baseball. He has to stabilize his scapula. If he didn't stabilize his scapula and his scapula was flopping all over the place as he was pitching, he certainly would have a very difficult time hitting the strike zone. So we have these stabilizing or fixator muscles that hold bones stationary. Skeletal muscle fibers are organized differently. When I say they're organized differently, they all have this epimysium, paramysium, endomysium, but how the fibers run can be different. And there's different how the fascicles run. Think of it that way. How the fascicles, surrounded by paramysium, within the muscle organ surrounded by the epimysium, how they run can be different. And they can run parallel, or they could be spread out in the beginning and converge on each other, or they could be circular, etc. So we're going to look at all these patterns right here. These are parallel muscle fibers. So they run for the most part parallel to each other. You're going to say, well, they converge on a tendon. Yeah, they do. But for the most part, in the belly of the muscle, this is called the belly of the muscle. By the way, some muscles have two bellies, so we name them that way, and you'll learn some of those names. So in the belly of the muscle, these fibers, these fascicles are parallel. So these are parallel muscles. These are parallel muscles. The rectus abdominis muscles are parallel muscles. And again, you have to look at the belly of the muscle because certainly they start to converge down on the tendon, the insertional or original tendon. But the belly of the muscle has parallel fibers. Okay, these are convergent fibers, and the classic example of this is the pectoralis major. So this is your sternum right here, just so you realize what we're looking at. And this pec major is hooked to your sternum, and this is going over to your brachium, your humerus, which is the area is called the brachium, just so you know. So this is the humerus over here, and this is the sternum, and this is your pectoralis major muscle. This is certainly a convergent muscle. Big, broad muscle here. Even the belly of the muscle has converging fibers. So it's wider on one side than it is the other. Okay, so that's and pennate muscles, feather-like muscles. They can be Unipennate, bipennate, or multipennate, and we'll talk about some classic examples of these. In your leg, you have oh, I'm switching to bipennate. I was doing the rectus femoris of your leg. Right here, you see. Let me do the bipennate while I'm doing it. This is the rectus femoris muscle. It's one of your quadricep muscles. This is bipennate, and you can see that from a central area, it's coming out from both directions like this. It's bipennate. All right. This is the deltoid muscle is multipennate. From up, if you look at right here, you can see it's going out in different directions from the place where we cut it. As a matter of fact, the deltoid muscle is so multipennate that what it does is it abducts the humerus. But depending on how you turn your hand, whether you pronate or supinate your hand, depends on what section of this deltoid muscle you use. So you can see the bipennate portion of the deltoid right here. Here's the center line, and here's the fibers coming off the center line. If you only looked at this part right here, you would think it looked like the rectus femoris. That's what you would think if you only looked at that part right there. But there's more than that part right there to the muscle. We have over here, and they also look like bipennate muscles. So altogether, this is a multipennate muscle. And then the extensor digitorum muscle is a unipennate muscle. It doesn't have another set of muscles coming off this center line. These aren't here like you would expect in a bipennate or further multipennate. What happens is these muscles just come off of one line and they go down into your tendon. So this is unipennate. Okay, circular muscles are called sphincter muscles, and you learned orbicularis oris and orbicularis oculi. There are a bunch of sphincter muscles that are made of smooth muscles we'll be talking about in the near future, but I'm not going to spend a lot of time on these circular muscles. They usually guard entrances and exits of body tubes, like your intestines or your capillaries or your eye socket, etc. All right, this is the big part that I wanted to get to. This is really why we do this part of Chapter 11 in lecture. Your muscle, tendons, and bones are a lever system. Simply spoken, that's what they are, is a lever system. And there's two types of levers. There's levers that have a mechanical advantage greater than one. And if you have a mechanical advantage greater than one, then you have a lot of power. But you have little speed. Versus if your mechanical advantage is less than one, then you have very little power, but you can generate a lot of speed. All right, we'll look at that in a second. So what's a lever composed of? A lever is composed of a fixed point or a fulcrum. So here's a fixed point. It's composed of the load or the resistance. And it's composed of the effort or applied force. Sometimes we call the effort the applied force. And there's three types of levers based on how the loads, the fulcrums, and the efforts are situated. A first class lever, as you can see here, the fulcrum is in the middle, and the resistance and the effort are on each end. This is a very rare joint in the body. Matter of fact, the only example I can think of is the atlanto-occipital joint. If you look right here, this is the only example I can think of. This fulcrum is the atlanto-occipital joint. It's the occipital condyle sitting on the atlas, C1, the atlas. And what happens is when you pull your trapezius muscle, that's the effort, you rock your head back. So the resistance is the weight of your skull, everything forward of the fulcrum. That's the resistance, the whole weight of your skull. So this is the first class lever, and I really can't even think of another first class lever, to be quite honest. They're very rare in the body. Third class levers are common. Second class levers are not uncommon. So first class lever, atlanto-occipital joint, is the only example I can think of. Now, second and third class levers have the fulcrum at the end. You can see the fulcrum at the end there and the fulcrum at the end there. So what's the difference between second and third class levers if the fulcrum's at the end for both of them? And the answer is where the resistance and the effort is. The resistance is in the middle for a second class lever. The resistance is in the middle for a second class lever. And the resistance is at the end for a third class lever. This is your classic, your third class lever is your classic curl. Your classic biceps curl, if you want to call it that. Third class lever is your classic biceps curl. Of course, your resistance is at the end. This is your dumbbell that you're hanging onto in your hand. All right. Let's go back to second class and talk about it. The resistance is in the middle. An example of this would be your tibio-talar joint. I'll use the example that's right here, by the way. And I'll draw the tibio-talar joint as well. Okay, so right here, this is my temporalis muscle. My temporalis muscle grabs a hold of my mandibular coronoid process and it closes my mouth. Actually, I'm sorry. We're looking at the digastric muscle right here. By the way, what I just said about the temporalis is true, but that's a different movement. To look at the second class lever, I have to look at the digastric muscle right there. The digastric muscle grabs a hold of my mandible and opens my mouth. It depresses my mandible. So my effort's right here. Well, where is my fulcrum? My TMJ is my fulcrum. Temporomandibular joint is my fulcrum. All right. Where's my resistance? Well, this antagonistic muscle to the digastric is actually my resistance. It's called the temporalis muscle. That's my resistance to the digastric. So my resistance is in the middle. My resistance is in the middle. My fulcrum's at the end. This makes that a second class lever when I'm talking about my digastric muscle. Now, let's do something else. What I started to do, actually. Let's talk about when the digastric muscle is the resistance and the temporalis muscle is the effort. Now the effort is in the middle. My effort's in the middle. My resistance is at the end. And that's a third class lever. So see, the TMJ fulcrum can be more than one lever depending on what muscle is moving. If you're closing your mouth with your temporalis, then you are using a third class lever. If you are opening your mouth with the digastric, then you're using a second class lever. All right. And then a third class lever is your typical biceps curl. What happens is you have a dumbbell in your hand right here and you're curling it. So your resistance is at the end. Your effort's in the middle because your biceps brachii insert onto your radial tuberosity. So your effort's in the middle and your fulcrum's at the end. It's your humeral ulnar joint. And that's a typical third class lever. This is showing you a first class lever, the atlanto-occipital joint. Same example, probably because this is the only example of this lever in the body. I mean, there might be another one, but I don't know it. I'd have to go through every single joint and think about it. This was actually the other example I told you, but I went with the picture that was on there. If you do a calf raise, that's a second class lever. Your fulcrum is the ball of your foot, your metatarsal phalangeal joint, your metatarsal phalangeal joint. Your resistance or load, remember sometimes resistance is called load, is right in the middle. It's your tibia coming down on your, it's your tibio-talar joint, in other words. Your tibio-talar joint is the weight of your body coming down on your talus. That's the load. And your effort is your calcaneal tendon pulling up on your calcaneus. So this is a second class lever where my fulcrum's at the end, my load is in the middle, and my effort's at the end. So that's another second class lever. And there's another third class lever, same example as we use, although there's other examples of third class levers. This is just a classic example right here. Now here's the important part. You can calculate a mechanical advantage of these levers. Mechanical advantage equals length of the effort arm over length of the resistance arm. Well, what the heck does that mean? You always measure from the fulcrum. So from the fulcrum to the effort right here is the length of my effort arm. That little purple bracket is my fulcrum to my effort. That's the length of the effort arm. And let's just say it's 50 millimeters. The length of my resistance arm, you always measure from the fulcrum, is from the fulcrum to your load or resistance right there. That's the length of my resistance arm. So what I do is I take LE, which is 50, over LR, which is 330, and I get 0.15. Well, remember what I said to you before. If a mechanical advantage is less than 1, then you have low power, but you have high speed. You probably already wrote that down. Let me just show you. You wrote it down right back here. If the mechanical advantage is less than 1, the bottom one here, you have low power and high speed. If the mechanical advantage is greater than 1, you have high power, low speed. So this mechanical advantage is definitely less than 1. All right, it's 0.15. So think of it like this, because this is how I think of it. If you were to curl 40 pounds right now in your hand, great, that's a good weight to curl one-handed. Put a lacrosse stick in your hand and hold it out, and have someone tie 40 pounds to the lacrosse stick, and now try to curl that. It would be much harder to do. And why is that? Because this lever doesn't have a mechanical advantage greater than 1. It's not a power lever. It's a speed lever. Which, by the way, is why we use lacrosse sticks playing lacrosse, is so you can increase the speed at which you throw that ball. But you can't throw a heavy ball. But you can increase the speed at which you throw that ball by functionally lengthening your forearm. And this is showing you another example right here. It's showing you what's the distance from my fulcrum to resistance right here. That's that distance, and they're saying it's 35 millimeters. What's the distance from my fulcrum to my effort right here to here? And they're saying it's 95 millimeters. Now it's LE over LR. That's what it is. So that's going to equal 95 over 35, which is about 3. I can't do that in my head. Well, actually, they did it for me right here. 2.7. So that's 2.7. Definitely greater than 1. So this is a high power, low speed lever. And think about that. You closing your jaws, or I'm sorry, at closing or opening, actually, you can do it both. You can open your mouth very powerfully. You can actually close your mouth very powerfully. So this is a high power, low speed lever, opening your mouth or your digastric muscle. This is just some examples of calculating mechanical advantages, and yes, you might have to do this on a test. So that was going to be your next question. So you have to memorize these 3 types of levers, and you have to be prepared to calculate your LE over LR and tell me what it means. Now, just so you know, I'm not going to give you a ruler on the test. So I'm going to have to give you distances of these arms. I'm going to have to draw in these brackets and give you distances. All right, folks, that's it for the muscle chapter. I'll see you in the blood chapter.